We can compute the binomial coefficients n choose k using n factorial, k factorial, and n minus k factorial. Or when n and k are small, sometimes we just use Pascal's triangle. You've probably done that before. Let me remind you how that works. So you probably used a trick to compute the coefficients of 1 plus x to the n, which we know are n choose k is next to x to the k, is the sum as k goes from 0 to n. Or some people memorize x plus y to the n equals the same sum as k goes from 0 to the n, n choose k, x to the k, y to the n, y to the n minus k. And that trick is use Pascal's triangle. Pascal's triangle is the table of numbers that has 0 choose 0, 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And you get it by starting with 1, 1, 1, and then you copy down ones on the outside. On the inside, you take the sum of the two numbers above it. So we've got 2. Let me see if I can make this line up better with the other triangle. 1, 1, 1, 1, 2, 1. 1, put the ones on the outside. 1 plus 2 is 3, 2 plus 1 is 3. And then put ones on the outside. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So these are equal. So instead of having to compute the ratio of factorials here, you could just draw this triangle and you get the right numbers. Now the fact that each of these numbers equals the sum of the two above it tells us that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. This equation is called Pascal's formula. And once we see this, well, it's natural to ask, why is this true? Why should the number of k element subsets of 1 through n be equal to the number of k minus 1 element subsets of 1 through n minus 1 plus the number of k element subsets of 1 through n minus 1? Or why should the number of binary words of length n having k ones be equal to the number of binary words of length n minus 1 having k minus 1 ones plus the number of binary words of length n minus 1 having k ones? So let's see why this works. So the left-hand side is n choose k, and let's look at this in the binary word, from the binary word point of view. So this is the number of binary words a1 through an with exactly k ones. Now to interpret the right-hand side in a way that we can see that it's equal to the left-hand side, let's suppose we want to write a binary word A1 through AN with exactly K1s. So if we want to write such a binary word, we're going to start with a 0 or a 1, because every binary word starts with 0 or 1. Actually, let me write 1 first. Let's start with 1 or 0. Now let's think about these two possibilities, and let task 1 be completing the word after starting with 1. How many ways are there to do that? So we need n minus 1 more letters. Including exactly k minus 1 more ones. So there's n minus 1 choose k minus 1 ways to do this. Let me put Pascal's formula up on top so we remember what we're trying to prove, and then I'll erase it below. N choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k. Now let's let task 2 be completing the word after starting with 0. So we need n minus 1 more letters. And we haven't put any ones down yet, so we need k ones. Now there's n minus 1 choose k ways to do that. Now if we create a binary word of length n with k1s, we're going to either start with 1 or 0. That is, we're either going to complete task 1 or complete task 2. And by the addition principle, the number of ways to complete task 1 or task 2 is the sum of the number of ways to complete task 1 plus the number of ways to complete task 2. That is n minus 1 choose k minus 1 plus n minus 1 choose k. And there we have it. So the left-hand side is the number of ways to create a binary word of length n having k ones. And the right-hand side has it broken down by number of words like that that start with 1 and the number of words like that that start with 0. So that's why these things are equal to each other. The end.